Welcome to our module on GPU-centric AI compute fundamentals. In this session, we will demystify the concept of east-west traffic, a critical architectural shift driven by modern AI workloads that is fundamentally reshaping data center networking. Let's begin by contrasting traditional network patterns with the demands of AI. Historically, traffic was north-south, meaning data flowed from a user outside the data center to a server inside and back. However, training large language models, LLM, requires a fundamental shift to east-west traffic. This is where servers inside the data center communicate constantly with each other. In an AI factory, training a model isn't done by one machine. It's a distributed computing problem where thousands of GPUs must act in unison. This creates a scenario where the internal traffic between these GPUs is orders of magnitude larger than the traffic leaving the data center. The diagram on the left shows the traditional model. A user sends a request north-south to a server. This is low bandwidth and simple. Now look at the AI factory on the right. Here we see GPU nodes 1, 2, 3 connected by thick bidirectional arrows. This represents east-west traffic. The nodes are constantly exchanging massive amounts of data with each other to synchronize the AI model, rather than serving a user. This internal chatter is what dominates modern AI network bandwidth. Exactly is there so much traffic? The answer lies in the size of the models. Trillion-parameter models simply cannot fit on a single GPU, therefore we must split the model and the data across thousands of GPUs. This technique, known as model parallelism, requires the GPUs to work in lockstep. After every calculation step or epoch, these GPUs must synchronize their results, sharing gradients and updated parameters. Often involves all-to-all communication patterns, where every GPU talks to every other GPU. This necessity to keep the distributed brain synchronized is what generates the relentless high-bandwidth east-west flows we see in AI. This flowchart illustrates why the traffic exists. At the top, we have a large AI model that is too big for one device, so it is split across GPU A, GPU B, and GPU C. Arrows between the GPUs represent the synchronization phase. You can see that GPU A must send gradients to GPU B, which sends to GPU C, and they all exchange parameters back. This creates a dense mesh of dependencies where data must flow constantly between all participants to keep the divided model functioning as a single intelligent unit. Not just the volume of traffic that matters, but its personality. Traditional cloud traffic consists of mice flows millions of tiny short messages like web page requests. AI traffic is the opposite. It consists of elephant flows, a smaller number of massive, sustained data streams that can last for seconds or minutes. These flows are extremely bursty, meaning the network goes from quiet to fully saturated in microseconds. The AI job cannot proceed until all data is received. A concept called tail latency. Even a single packet drop or delay on one of these elephant flows can stall the entire supercomputer, wasting valuable GPU cycles. This Gantt chart visualizes the bursty nature of AI traffic. The blue bars represent compute time, where the GPUs are crunching numbers and the network is quiet. Suddenly at the 5-second mark, hit the red network burst phase. Both GPU 1 and GPU 2 simultaneously unleash elephant flows to synchronize data. This creates a massive spike in east-west traffic that saturates the network links. Once the burst finishes, they return to computing. This cycle repeats, demanding a network that can handle these sudden, synchronized shocks. Handle these massive east-west flows, we need specialized infrastructure. We use RDMA and row CA RDMA over converged Ethernet to allow GPUs to write directly to each other's memory, completely bypassing the CPU and OS kernel to minimize latency. We also use rail-optimized topologies. Instead of a random mesh, we wire specific network cards to dedicated switches, adding streamlined rails for data to travel without contention. Finally, we employ adaptive routing. If one path is clogged by an elephant flow, the switch intelligently sprays packets across alternative paths to ensure the data arrives on time, maintaining the lossless behavior required for AI training. This diagram compares the data paths. The top path shows the inefficient standard path, where data must hop through CPUs and system RAM, significant latency. The bottom path illustrates the optimized RDMA path for east-west AI traffic. Notice the direct, thick line connecting GPU as memory to GPU BS memory. By bypassing the CPU bottlenecks, RDMA allows the massive east-west flows to move at the speed of the wire, which is essential for keeping high-performance GPUs fed with data.